Is that the one I just turned in? Or is that the one?
Friday last week?
Did I turn it in?
I can tell you here in a second.
Because I have this here sheet, and I don't think I ever turned it in.
Put it.
Yeah, we did.
We did?
Yeah, we had Friday.
We're gonna be honest.
Thursday.
Because that was
Thursday we didn't play.
Well, that was when I turned on Monday. I said, what was this doing? You're like, I don't know.
Friday.
So,
I think it was Friday. It must have been Friday.
So I should turn it in, is
Probably.
what you're saying, right? Good idea.
Okay, alright, let's talk about number one here. So if you're writing down that property with a constant, where you have the b there, and I factored out a b. So in this case, I factored out a 3. What you do is, once I pull the 3 out in front of the limit, we can evaluate limits at numbers. So like for instance, you're always allowed to do this to try it for the first time to see if it will cause any problem. Can I plug a 2 into this function right here? Will it cause any problems? Will like I divide by 0?
No.
So it looks like I'm plugging in, right? So if I plug in a 2, because it's not going to cause a 0 on the bottom, because there's actually there's no fraction in the first place, I can actually plug that number in, and here's what I get. If I actually plug the 2 into that function, I'll get 2 squared plus 2x. And again, why I'm plugging in 2, they're telling me what number they want me to evaluate at. So that's why I'm approaching 2. I'm just going to plug it in. So that's 2 squared plus 2 times 2. So if I actually do that, and plug in my number, 2 squared, that's 4. 2 times 2 is 4. We're going to add those together and then take it times 3. And the answer is what, 24? That's 8 times 3. That's what your limit is approximately. If you look at the graph of this thing, at the number 2, from the right and left side, we'll look at graphs here in a minute, the number should be approaching number 24 on a graph. Shh. So, now, if you didn't happen to pull it out, let's say you didn't pull out the 3, you didn't even notice it, it's not on your radar, you didn't even know you could do that, you could have just plugged the 2 into the original problem anyway. So if I just went to this problem here, just plug in the 2. And so right here, if I just plug in a 2, that's 3 times 2 squared plus 6 times 2. Because again,
So why would you ever factor some of that out?
it's when you have variables and you can't get rid of the variables. So we're going to see it in a little bit. We'll do one where you can't actually like factor out anything, but if you take the numbers out front, you can actually evaluate a function. We're going to look at, I think it's my 3rd or 4th example we're going to look at.
Okay.
That'll work that way. I can't do it right now because we need to get to number 4 before I show you that example. Like we're going to mix these properties all together, and this will explain how to evaluate one. Yeah, but I'm going to get to your question. So, all right.
Wait, are we supposed to write down this property of the limits?
Yeah, you should be writing these 6 down.
Oh, I didn't know
Okay.
that.
So if I evaluate this, that's 4 times 3, and then 6 times 2 is 12, and then this turns out to be 12 plus 12, which is 24. So as you can tell, the answers are the same. Do you agree that they're the same number? Now, to get to what Nicole is asking, it's like, why would you do that? Like, it's giving you the same answer anyway. There's a problem that we're going to see, it's 3rd or 4th example today, where you actually have to pull out the number out front, you have to factor out a digit, because you will never be able to evaluate the function. It keeps telling you it's going to infinity in certain parts. And so it's kind of important that you actually do pull that out. But I want you to at least see one of these, like where you can do that. You can pull out negative signs. It's the same idea. Like one of the second pictures I'm going to show you here in a second, it'll have a negative sign. You can pull the negative sign out front because it's a -1, because that's just a constant. Remember, you only do this with constants, not variables, by the way. Just constant numbers. Okay, are we good with rule number 1?
No.
No, Lord, I wrote down all the rules. I didn't know what was going on.
Okay. Do you have that written down?
Yeah,
No, I wrote down the rules. I just finished the rules.
I just finished writing all 6 down.
Alright.
Explain to me what's going on over here.
Okay, well, they gave you a problem. And if you notice that they all have a number in common, you can pull that number out, like factor it out. And then that can go outside of your limit. And then you can just do the limit as normal. You would choose to do that in certain situations where you can evaluate limits. And we'll see one of those a little bit later.
What is that X goes to C up to go on?
This thing?
No, I supposed to see, yeah, that.
Up on
Up
the
on the board.
properties.
Oh, this?
Yeah.
This is your X, it's your variable using, and this can be any number you want, any constant number you want. Is what C is.
I'm
Oh,
gonna write that every time.
okay.
So it's C is a constant, some digit. You're going to evaluate to 2. You're going to evaluate it to 0. It could be any number.
Oh, okay.
Okay. All right. Now, second rule, and this second rule can still apply to this problem. That's why I kind of picked this problem as my go-to. On the second problem, you can now do the second rule, where if you're adding two items together that you're trying to take the limit of, you can now separate them into their own limits. Like, you can put the limit on both functions that you have that you're trying to add or subtract together. Again, it works for subtraction too. And then you can evaluate those limits separately. So we already know the answer to this problem. This answer is 24.
Please don't erase that.
I'm going to leave that problem. This stuff's going away here in a
No,
second.
No, I don't.
Right over there. Over there.
Where?
Not
Look
sure.
at all these gobs of marker boards.
No, just that whole thing.
No,
that
Ward.
whole big space.
Can you
Right
just
there.
like
Use that.
slow down
Yeah,
for a
go
sec?
over.
Mr. Ward, just go back there.
He's going. He's running from right to left.
And Mr. Ward, you have all this marker space, so you don't actually use it.
Yeah, not yet.
One.
Okay, well, I'm trying to write this down.
I don't know. It's pretty much all.
I can't. I can only write so
Hey.
fast. Jeez. Chill out.
Just not.
Or you can watch his videos that he posts on MrBoard.org.
I
Yeah, but
think
if
I
you
have
can't,
time to do
if
that.
you went on a different marker board, we couldn't see the thing, so you better just stay on the first marker.
All right.
We can still see him right
Yeah, you can't see the stuff in the
So,
camera.
Okay, first, I'm gonna do the second rule, same
Oh.
exact rule, this is example number 2 of that thing. So what we're gonna do is we're gonna separate these into two separate logarithms. We can still plot the number 3, you can still do those same rules as rule number 1, but what this one says, if you're adding or subtracting functions together, you can now separate them into two separate limits. So 3x squared plus the limit as x approaches 2 for 6x. Like, you can separate them into their own limits and calculate them separately, and then you can add the two answers together or subtract them. So, does everyone see that these are the two functions that I'm adding together? So that's what I'm doing. I'm taking the limit of both of these separately with the same number. This digit just repeated twice. And since you can take out numbers, you can do whatever the rules that we have on here, but I can now just evaluate these separately because maybe that makes the problem easier to look at. So for instance, if I want to plug in 2, will it cause any problems if I were to plug in 2 into that problem? Like, will I divide by 0 or anything like that? No. So it's going to be 3, 2 squared, because I just plugged in 2, it didn't cause any problems. I'm allowed to do that if it doesn't cause problems. Over here, I can plug in the 2, it doesn't cause any problems, so that's 6 times 2, because you just plug in the 2 into all the x locations. So this turns out to be 4 times 3 plus 6 times 2, which is 12, and this is 12 plus 12, which is still 24. So the reason I'm showing you this is that these rules are helpful in certain situations when you can't just look at the overall problem and just calculate the limit of it. You have to separate it into parts so you can see what's happening. Now, it normally makes more sense when you're going out to really big numbers, not just really easy things like 2s. Usually you do this for problems when there's actually like issues where you can't plug a 0 into the bottom. You want to try to figure out what's going to happen in those situations.
Does that limit thing go away on the bottom?
Yeah, so the minute you plug these numbers in,
You don't have to.
then the limits are, you're evaluating the limit, you don't need to write limit anymore.
Okay.
Yep.
So we have to write the limit.
You have to write the limit until you plug that number in.
We just draw a arrow.
Okay, no, they want you to keep writing. That's the way I always
They
write
want
it.
you.
So you have to you always have to carry it down. So, nope. I want you to have good mathematical practice, so no, you have to carry it.
Thank you.
Okay, all right, we good with example number 2?
Not really, but yes.
Okay.
No.
Why do they have periods at the end of this? No.
You're clear as mud. Oh yeah.
There's periods at the end of all of them.
Yeah, there's supposed to be things like this.
Those are sentences.
All right.
Complete.
That's the beginning element.
All right, rule number 3. Rule number 3, if you're multiplying items together, you can separate them into their own separate logarithm, or separate limits, sorry. So here, we'll do example number 3. And I'm just going to do a piece of the example that we're doing. So example number 3, I'm going to just do the limit as x approaches 2 for this part that we had on that problem. That was the first part, when we separated these into their own limits. I'm just going to do that first part. Do you agree that these two items, 3 and then x squared, are being multiplied together?
Yeah.
You can separate them into their own limits, like limit as x approaches 2 of the number 3, and multiply that onto the limit as x squared as x approaches 2. Like, you can separate them into their own limits and then multiply those limits together.
Why would you want to do that?
In case the items you're multiplying together are really big parentheses, like you
It's
don't
like
want to foil
blocks.
everything together, they're just really big, you can separate them to their own and then evaluate each one separately, because maybe like if you were to separate them, they won't cause any problems, you don't have to like do this crazy like Pascal's triangle where you have like powers of 7s and things. You can separate into separate
Where
logs and
did
do the
Pascal's
numbers.
triangle go?
Yeah, I erased it, we just didn't get
Mr. Ward, it's like logarithm.
Oh, this is the
it. Yeah, almost
It's
almost
still-
identical.
Think about
Okay.
all the math that's on.
All right. Now, that's the product rule. Quotient rule, same thing, I don't even know if I need to write it. If you have two items being divided, you can separate them to their own logarithm. This is something that we're gonna look at later. This is the one that Nicole was hinting at, like why would you pull out a number? It's gonna be, that would be the example I'm gonna use, number 4. And then number 5
I still don't
is,
get how that changes anything for number 4.
oh, you'll see. You'll definitely see it on this next one. We have coming up. So the third, fourth example, so I'm gonna answer Nicole's question, your question here in a second. With that one, with number 4, why do you want to separate them? Number 5 is how I actually keep going on this problem. So, this part right here, this is example number 5. If you're gonna take a limit of a constant number, like just a k, a number that's in there, the answer, they always say if you're taking a limit of just a constant, it's just the constant itself. So this answer would just be 3. That's the idea, because there's no x to plug the 2 in, so you're not actually multiplying anything, so it's just the number you have. And then we're gonna take it times whatever this limit is, where you'd have to evaluate this one separately. But this was a constant, so the answer just carries down. You're gonna see that, that's one of the examples we're gonna use. And then the last one, same idea. If you just have a limit of an x, just a plain x, so you separate everything out to just single x's, you could plug that number into the x and then actually evaluate it. So it would just be the number c. Or whatever number c is, I should say. Okay, questions with the 6 rules. Now we have to mix these kind of all together into problems to actually evaluate things, and that's when we have to learn different strategies. Some problems are so difficult in nature that our rules here, we just have to just plug in numbers on a table and evaluate them, with just approximating the number that we're approaching, and just go from the right and left side, plug in a couple decimals here and there, and actually approximate. I'm going to try to show you examples today of where you can do this stuff and get answers. Okay, some of these will be a little bit weird, but I'll try to show you some different examples. So let's get to the first ones. My last thing I want to end with today is graphing. I want to talk about graphs again one more time, because that's what we did yesterday. Anyone still needs these examples on board? Okay, perfect. Somebody want to wake up Sid? She's sleeping. Don't sleep, Sid. Don't want to
You
sleep
woke
right now.
yourself up.
All right. Okay. All right. Okay. First example. Now, hopefully you have those rules written down. First example I want to do here. Let's actually get to the problems. All right. Okay. Okay. Here, right here. This is my function. So, let's say that I want to evaluate this function at the number 5. At the number 5. So, I want to do the limit as x approaches 5 for negative x to the 4th. I want to show you how every rule works on this problem that I can apply to it. So, number 1, I can take out a negative sign. So I'm going to take out a -1 out front. So I take the negative. So I know my answer in the long run will be negative as long as it's on the outside. Now the reason why I know it's negative, do they have a parenthesis around this? Shh. Do they have a parenthesis?
No.
No. If they had a parenthesis like this, the answer is probably going to be positive, because the negative sign will go away with the power of 4. But since they didn't have a parenthesis, my answer will be negative, and that's the reason why your calculator, if you were to type it in something like that, it actually tells you it's opposite, because it's doing that situation. Now, the rest of this, I could plug in the 5 and I go 5 to the 4th, or you could do the power rule, which means that there's 4 of these x's being multiplied together. That's what it actually means, with x to the 4th. And then you can apply the product rule, the rule we just learned a little bit ago, that if you have multiple items being multiplied on the inside, you could separate them into their own limit, I should say, not logarithm, but limit. And you can multiply each limit together separately.
Did you just make up the
Did you just
five?
make up that 5?
No,
Where's
why,
5? Yeah, I just made up
Where's
that
the
number. They're gonna have you just evaluate random numbers.
wait, so why wouldn't you just put,
You could just plug in the 5, go 5 to the 4th, put a negative sign out front, done. But I'm showing you like how you can apply your properties.
We
Okay,
can just.
this is an easy one. We're gonna get to the more crazy one.
Wouldn't that be way more simple though, if you just plugged it in?
Don't get me wrong, like on this problem, yeah, it's kind of simple. My goal is to show you what the properties are and how to apply them.
Oh.
Okay, we'll get to the difficult ones. Like I still need to
I don't
answer
think we have
those
to.
questions.
No,
Okay.
we could just not do the difficult ones.
No. All right,
Can't tell you what answer is.
x to the 5th, x, limit, x to the 5th. Okay, all right. Then you can plug in the 5 separately, so you're gonna have 5 times 5 times 5 times 5. The negative sign's out front. You get your final answer, which is like 625 or 525 or something. All right.
Yeah.
Questions on what the properties are and how to do it? Okay, let's just jump. I'm gonna jump past the next one. It'll be the same situation. I want to get to the question that Nicole and Reese keeps asking. This one.
Or, I don't have really fast.
tomorrow?
Yes.
All
right. Now, hey. So, we're gonna do the same thing. We're gonna find the limit of this problem, but now here's the difference. This is where this is gonna take a lot of like common sense thinking about this problem. It's not gonna work out nice and pretty, but I want you to see this for the first time. I want to evaluate this problem. This is a rational problem. It's a rational function. It's got numbers on the top and bottom, variables. I want to try to approximate what this limit is if you were to approach infinity. So not just a number. I want to know what the limit is as x approaches positive infinity. So you'd be plugging in bigger and bigger numbers into this problem.
How do you plug in infinity?
Okay, that's the problem, right? So now you have to resort to knowing what this is going to cause in this problem. And this is going to take a lot of like common sense, and just, this is one way to evaluate. It's just one of those things, you just need to see it. Okay. Now, we could separate these into their own limits, top and bottom, and go from there, which I'm going to do here in a second. On the top, do they have anything in common?
3.
A 3. I want to pull out the 3 out of that problem. So I'm going to separate these into their own limits using the quotient rule. So it's going to be this. Limit as x approaches positive infinity, and I'm going to pull out a 3 out of the top. Okay, does everyone see how that worked on the top?
Sure.
Okay, I'm going to pull the 3 out front here in a minute using that scalar multiplier rule. On the bottom, it doesn't look like they have everything in common, but here's the weird thing. What I'm going to tell you to do is take out a 5. Even though the 12 doesn't come out that number clean, I'm going to take out the 5. I like to take out the number that's in front of the leading coefficient. So like on the top one we took out a 3, on the bottom I'm going to take out the 5. So I'm going to go the limit as x approaches positive infinity. I'm taking out a 5 out of the bottom. Now when I take out a 5, I'm dividing the 5 out, so that's x cubed, 5x. And when I divide a 5 from the 12, that's just 12/5. Now, I know that's a decimal, it's fine. Okay,
It's fine.
now, next step. So what I did so far is I did the quotient rule. I took out a constant multiplier, scalar multiplier, and now I'm going to dump those numbers out front. Because these numbers can go out front because of that scalar multiplier rule. That was rule number 1. You could throw the number out front of the limit as long as it's a constant and it's being multiplied on everything that's on the inside. So, what I have here is I have this. I have 3 and a 5 out front, 3/5, being multiplied on 2 different limits. The limit on the top, which is x cubed plus 2x squared plus 15. And on the bottom, and this is as x approaches infinity, and the bottom is the limit as x approaches infinity for x cubed plus 5x plus 12/5. Okay, now here's the goofiest part about this.
You're playing back in.
Okay, most people have this trouble, like you're plugging in infinity. Infinity is a direction, it's not a number. But what this is, this represents really, really big numbers, right? So like thousands, millions, billions. And you're going to be plugging them in here. If I were to plug in really, really big numbers, what happens to this problem? It just gets bigger and bigger, right? So as you go towards infinity, as you evaluate towards infinity, you plug in just bigger and bigger numbers because that's the number we're trying to approach. This top is approaching infinity, positive infinity. That's the number it's approaching. It's a really big number on the top. Out front, we still have that 3/5. On the bottom, I'm going to be plugging in bigger numbers as well, like numbers that are approaching infinity. So like thousands, millions, billions, trillions. Sure. And eventually, what happens here is you plug these numbers in, these numbers on the bottom also get bigger and bigger and bigger, and they approach positive infinity. They're not going to be negative numbers, they're positive numbers down there.
What?
So, what you're looking at is I just evaluated the top and bottom separately. I could have even went to the different rules where I separated each one separately. But what happens when you take infinity, like a really big number, divided by infinity, a really big number? It goes away, it turns into 1. If they're about the same number, because they're so big anyways, they're nearly the same digit, they eventually will cross each other out because these will divide to make the number 1
Times 3/5.
times 3/5. So your final answer, the limit of this thing is just 3/5.
That is just stupid math.
Now, this should make sense if you think about what we've learned in previous years, pre-calc, what we did in the very first chapter of this textbook, that when we had a problem ignoring the limits, and I asked you, like, if it was a rational problem, to graph that thing. You had to look first for any x-intercepts, y-intercepts, then you had to look for symmetry, and this problem had horizontal asymptotes. They had powers that were about the same number. They were the same digit, right? X cubed over x cubed. The rule was to figure out where the horizontal asymptotes are. If the top's bigger, you don't have any. If the bottom's bigger, it's always at 0. But if they're the same power, the horizontal is going to be at 3/5. So here's 3/5 on a graph. These tails, as you go to infinity, out this direction towards positive infinity, are going to hug up right against that horizontal asymptote, and that's why the number is 3/5. So it's actually using things we did in the previous sections, but it's applying it to a real life situation where you don't have a graph anymore, even though I applied it to a graph. You have to think about what we've learned and how to apply it still. So like knowing that this thing had a horizontal asymptote, I could have told you the limit before I started because they had the same power. If any of these powers are different, then you have to think about what is that approaching. The bottom number might be getting too big versus the top. The top might be a really small number, the bottom might be really big. Well, what do you get when you take a number divided by something huge? You might get a number like 0 almost. I mean, it's approaching 0 to the most part because it's still following this rule. Where's your horizontal asymptote? Where are the tails going? If the tails are going up and down, then you know it's going towards infinity or negative infinity. But if they're leveling off, like the things we learned in the first chapter, you can now apply it. But does everyone see the rule? So Nicole, to answer your question, why would you ever take out a number out front?
Yeah, so you
That's
can
why.
separate it.
So you can actually evaluate a problem and know exactly what answer it's supposed to be. Without doing that rule, we've never been able to evaluate this thing.
So if they're the same, can you just go 3/5? Answer.
Yeah, I mean, I could literally look at that problem. If I know that the powers are the same, it's 3/5 is the number out front.
So if you assign us that problem, can we just write down 3?
Yes.
Okay.
You know the limit. So let's do another one. Let's make up any problem we want, any powers we want.
17,000.
We want the same exact powers.
4.65 million.
Same powers.
Same powers. So that
Same powers, so x to the third.
Efficient.
What?
X to the third, give me some number out front.
17,000
Oh, no.
over 386,234,167.
386 million,
No, I didn't.
246,612.
612. All right, and we could add anything back here. I don't even care what these things are. Okay? All right.
What if you're subtracting something? Does it matter?
Make that like
Doesn't matter.
8 million X.
The powers are still the same. And so the rule is we would still do the same process. You would still factor out that front number. You would still evaluate the limit. And these numbers, since those numbers we'd be taking out, these would go to the front.
Wait, I have a quick question. What if the powers are different?
If they're what? If they're different, that's the ones we need to look at. What would happen in that case? 3, 8, 6, 2, 4, 6, 6, 12.
Do you know what that number represents?
Population US?
Absolutely not.
No. Okay, there. That's your limit as we approach infinity. It's the leading numbers because they have the same powers. Now, to get to Nicole's question, what happens when the powers are different?
I'll give you some more numbers.
I thought you said you had it on Sunday.
When the powers are different. Let's, there it is. Powers are different.
Yeah.
It's honestly probably close though.
Yeah, you don't need to be sure.
What if it was perfect?
Okay.
I don't.
All right. So, what happens when the powers are different? Here we go. Limit as x approaches infinity, and the powers are different now. And yeah, they kind of try to trick you with putting these out of order. All right. Do you agree the powers are different? Okay. In a normal, in a normal graphing problem that we had in the first chapter, you'd have to look at where's the horizontal asymptote going to be. Well, in this situation, since the bottom turns out to be bigger than the top, the bottom turned out to be bigger than the numerator, we would have on the graph, if we were going back to the first chapter, you would have a horizontal asymptote, a semi-permeable selected membrane, whatever you called it.
Selectively permeable.
There you go, that one. You would have that membrane right at 0. Because if the power is bigger on the bottom, it's always at 0. If the power on the top is bigger, you don't have a horizontal. If the power is exactly the same, it's wherever that number is, the leading coefficients divided. That's why the limit was always that number. Well, in this case, my horizontal is at 0 because do you agree that the power is bigger on the bottom?
Yeah.
Okay, so as you go to infinity, whatever should happen here, your graph, whatever it's doing, should be hugging up against it. So as I go towards infinity, what number is it approaching?
0.
0. I knew it instantly before I started. The actual limit should be 0. Because what's going to happen here, if you were to actually divide these, or like simplify them as far as you can, this is basically the concept of what you're dealing with. The power on the bottom is always 1 bigger than the top. So whatever the top is, it's a small number. These are growing faster on the bottom because they're 1x bigger. And so what's happening here is this goes to infinity, and it's outpacing the top by a lot, that it's eventually going 1 divided by a really big number, which is really, really close to 0. And that's the concept. Okay. Questions at all? Now, this is a completely different beast if I were to go back to this problem I did earlier. Let's see. There we go. If I were to go back to this problem earlier, this problem is a completely different animal if I were to try to go to infinity. The reason being,
No, it's not. Chupacabra.
okay, so if I'm supposed to be going to infinity on this problem, you have to think about what the graph's doing. What does the power of 4 graph look like? What do the tails go?
Same side.
Same side. Since it's negative, what happens?
Goes down.
So what's going to happen here, this is the generic look of what this thing's doing. It's turning 4 times, right? 1, 2, 3.
That's 3.
1, 2, 3. There. 3. Okay, it's 3 turns, right? 3 actual turns. So what happens as you approach positive infinity this direction, this graph is going down. So the actual limit as negative x to the 4th power approaches infinity is negative infinity, which means it doesn't exist.
Yeah.
Because negative infinity is not a number, so the limit it never stops. You can say it's approaching negative infinity, but the limit doesn't actually exist in the first place.
Do not eat.
Okay, questions?
That's the gag rule.
All right. Okay, hey, last problem here. I want to go back to what we did yesterday.
No more than freezing out.
Okay, I would like you to draw this graph in your notes, just a rough sketch of it.
A rough mock.
Rough sketch.
A mock. This is where my rough sketch.
This is my last problem today.
Do you ever get a little sad when it's the last problem in your
Do you wish math went on forever like infinity?
Sure.
It does, actually.
Okay.
Math
Math will
Okay.
end someday.
All right. Hey, I have a couple different questions for you.